Hello and welcome to Honors Function. This is the second video on inverse function, and in this video we're going to be answering the questions that we asked ourselves in the first video. The first one is, when do I know if a function has an inverse or if it doesn't have an inverse? And the second question is, if it does have an inverse, how do I find its expression? Okay, so let's start answering the first question. So let's look at an example when a function does not have an inverse. For example, I'm going to be taking the function f of x equals x squared, and this doesn't have an inverse, and that's easy to show. Let's see. If the input is 2, what's the output? 4. Okay, and then if the input is negative 2, what's the output? It's also 4, right? And there are other points, of course. In this function there's an infinite number of points. But what happens, so this is for f, what happened when you look at the inverse relation? Okay, this is the inverse relation. What happened when you look at the inverse relation? You're gonna find the point 4, 2 and the point 4, negative 2. Therefore the inverse relation is not a function, right? The same input goes to two different output. It doesn't pass the vertical line test. So because the inverse relation is not a function, then we say that f does not have an inverse function. That's what we say, right? So how did we really understand this? You have to flip the coordinate, right? So suppose you have here x1 and f of x1, right? And then another point, x2 and f of x2, right here. So how will you know if a function has an inverse or not? If you flip the coordinate, here you would have f of x1 and x1, and then you would have f of x2 and x2, right? So if you have an equality of the inputs there for two different outputs, right? If you have f of x1 equals f of x2 with x1 not equal to x2, this is when f does not have an inverse. F does not have an inverse function, right? So another way of saying this is, how can you guarantee that it has an inverse function? You can guarantee that it has an inverse function if f of x1 is equal to f of x2, right? If f of x1, if you take an equality of the input in the inverse relation, this is an equality of input in the inverse relation, then you have an equality of output. Then x1 equals x2. So this is the equality of output, okay? Writing this a little bit more mathematically without the words here, we write f of x1 equals f of x2 implies that x1 is equal to x2. It means the same thing. This is a conditional statement, if then, okay? If this is true, we call f is 1 to 1. F is 1-to-1 function. This is a definition of a 1-to-1 function. Okay, this is a definition of a 1-to-1 function. Definition. Okay, so what is a 1-to-1 function? A function for which an equality of output implies an equality of input. What about the other way around? What do we call a function for which an equality of input implies an equality of output? What does that mean that x1 equals x2 if implies that f of x1 equals f of x2? Well, guys, this actually means that you got a function, okay? That's just a function, all right? It means that if you have an equality of input, you cannot have two different outputs. So, for example, right, if you look at the axis right here, you have the x-axis. Here, I'm going to call that x1, and I'm also going to call it x2, and I couldn't have f of x1 right here and f of x2 right there. It wouldn't pass a vertical line test. So this is just something that we call a function, right? While this is more than just a function, this is called a one-to-one function. And as we just mentioned, a one-to-one function is a function for which the inverse relation is also a function. So this will mean that f has an inverse function, okay, because its inverse relation will be a function. That's the reason why it has an inverse function, because its inverse relation will be a function. Remember, these are points in the inverse relation, okay? Let's think about it graphically. What does it mean graphically? Well, it means that, check it out, we know what y equals x squared looks like, right? It goes like this, right here, goes like this, right there. So we have an equality of, oh, I've lost, right here. So here's 4, right there, and here's 2, and on this side you got -2, right? So this is the graph of y equals x squared, and it does not have an inverse function, or another way of saying that, its inverse relation is not a function because this output of f, shoot, it keeps on moving away. This output of f has 2 different input associated to it, right? 2 and -2. So we say that the graph does not pass the horizontal line test, okay? So a graph that will have a function that will have an inverse function will have to pass the horizontal line test. Intuitively is, look, if you're at 2, where do you go with f? You go to 4. But then when you are at 4, you don't know how to go back uniquely, right? Look, 2 goes to 4, but then you don't have this arrow back right here. Why? Because you have 2 possible arrows back. One to 2 and the other one to -2. And therefore, you don't have an inverse function because there are 2 paths from 4, right? I hope it's clear. So we say that a function passes, f passes the horizontal line test if, oh, right here it would say does not pass, right? Here it doesn't pass. It doesn't pass the horizontal line test because a horizontal line will cut the graph in more than one places, okay? So again, guys, the vertical line test is to decide if you have a function. Yes, this is a function. The horizontal line test is to decide if your function has an inverse function, and this one, it passes the horizontal line test. It has an inverse function, all right? So we covered 3 results. 2 definition and 1 statement. Let me go to my note to show you the 3 results. Here we go. First definition, a function is one-to-one if an equality of output implies an equality of input. This is an analytical statement. Second definition, a function passes, we say a function, not the graph, a function passes HLT if a horizontal line issued from any value in the range of the function intersect the graph of the function in exactly 1 point, okay? Exactly once, okay? So these are 2 definitions, and then the result, the theorem, a function is one-to-one. Oh, I'm sorry, there are 2 results right here. Sorry. A function is one-to-one if and only if it passes the horizontal line test. So this is a graphical statement, right? And these 2 are the same. They are the same statement. One is looked from the point of view of the graph, and the other one is an analytical statement, but it means the same thing. These 2 statements are the 2 sides of the same coin. They are equivalent. One is an analytical statement and the other one is a graphical statement. They mean the same thing, okay? Now, a function is one-to-one if and only if it passes the horizontal line test. Okay, got it. And the second one, which is the answer to our first question, a function is one-to-one if and only if it has an inverse. So now I know when a function has an inverse. If it's a one-to-one function, that means two things. Either it's one-to-one, or this is the same thing as it passes the horizontal line test. Alright guys, let's go over some examples now. Example number 1. Show that this function is one-to-one analytically. So you have an equality of output. You have to show that this implies an equality of input. How do we do that? Well, let's take an equality of output. x1 plus 1 over x1 minus 1 equals x2 plus 1 over x2 minus 1. Why would this imply that x1 equals to x2? Well, we don't have a lot of choices here. We need to do the cross multiplication. So x1 plus 1 times x2 minus 1 equals x2 plus 1 times x1 minus 1. Okay, got it. Let's expand. So we have x1, x2 minus x1 plus x2 minus 1 equals x2, x1 minus x2 plus x1 minus 1. So this goes and this goes. Now what do I have? I have that, let me see, negative x1. So I'm going to move all my x1 on the same side, right? So I would have negative 2x1 equals negative 2x2. Oh, okay, well, that means that x1 equals x2. Got it. I proved it analytically. This function is one-to-one. Therefore, it has an inverse function. Please do example number 2. I'm going to do example number 3. I'm going to show that this function is not one-to-one analytically. So let's take an equality of output. F of x1 equals f of x2. And let's see why it doesn't imply that x1 equals x2, right? So that means that x1 squared minus 2x1 equals x2 squared minus 2x2. All right, what do we do with that? I'm going to move this here and that there. So I have x1 squared minus x2 squared. Actually, let me move everything on the same side, okay? So actually, I'm going to move this there. I'm not going to move this one there. I'm going to move everything on the same side. So I'm going to keep the negative 2x1 here, and I'm going to say plus 2x2 right here. Okay, got it. Let me factor. I'm going to factor this term right here. x1 minus x2 times x1 plus x2. And here I'm going to factor 2 minus 2 times x1 minus x2. Okay, we can factor further, right? I'm going to factor x1 minus x2 now. So what do I have? I have x1 minus x2 times, okay, times what? Times. So x1 plus x2 minus 2 equals 0. Now, when is a product equal to 0? When one of the two terms is 0. So if x1 equals x2, okay, got it. That would mean that f is one-to-one, but there is a second condition. Or x1 plus x2 equals 2. And that doesn't mean that x1 equals x2, right? That means that x1 is equal to 2 minus x2. So we have two possibilities here. We don't have just that x1 is equal to x2. We don't have that, right? So this function is not one-to-one because we were not able to prove that it implies that x1 equals x2. Yes, it could, but it can also mean that x1 is 2 minus x2. So which one is it? We cannot sort them out. Okay, it can be this or it can be that. So it's not just this. All right, is it clear? All right, please do number 4. I'm asking you to show, decide whether it is one-to-one. Hey guys, think graphically for this one. It should be done in 2 seconds. Okay, well, maybe a little bit more for the argument, but this is very short. Okay, next example. So in the next series of examples, I'm giving you functions that are one-to-one. They all have inverses. All of these functions have inverses, okay? And I'm asking you to find the inverse of the function. So this is pretty easy, right? Look, let me replace f of x by y. This is my function, the given function, right? This is my given function right here. Okay, now how would you find the inverse function? Well, we know what it is. You switch x and y. So x equals 3y minus 5, and then you solve this equation for y, and that will give you the expression of the inverse function. So this is very simple. X plus 5 equals 3y, and so that means that y equals x plus 5 over 3. What's it? Please always go back to the notation. F minus 1 of x equals x plus 5 over 3. Here we go. That's it. This is the expression of the inverse function. Okay, so switch x and y and solve for y and go back to f minus 1. All right, let me do another one. Actually, this is very important. You need to be able to do this one. This is not going away. This is a kind of example that's going to show up in many places throughout the year. Okay, so this is very important. All right, so here's a given function, x plus 3 over x minus 4. I want to find the inverse function. So switch x and y. X equals y plus 3 over y minus 4. And now you need to solve for y. You see y is here and y is there. How are you going to solve for y? Solving for y means that at the end I need to have y equals, right? How are you going to do that? Well, here we go. Here's the steps. Maybe you want to pause the video and try it on your own, but let me show you the steps right here, and you're going to do number 7. You multiply by y minus 4. It's kind of very natural, okay? I multiply by y minus 4 both sides to get rid of my denominator. So now at least my y's are at the same level. Here they were numerator and denominator. Here they're on the same line. But now I have to have them on the same side. But before I grab this y, it's involved in the multiplication. I need to expand this side. So xy minus 4x equals y plus 3. Good. Now I can grab it. And actually the one I'm going to grab is this one. I'm going to move this there. And this I'm going to move there. All my y's have to be on the same side, right? So I have xy minus y equals 4x plus 3. I am so close. I am so close now. I want to solve for y. What do you do? What do you do? This is where students hesitate sometimes. Hey, solving for y means y has to appear only once on this side, right? So what does it mean? It means you're factoring it. So it's y times what? X minus 1 equals 4x plus 3. That's it. We're done. Now I can solve for y. 4x plus 3 over x minus 1. Don't forget the last step. Right. F minus 1 of x equals 4x plus 3 over x minus 1. Here we go. That's how you find the inverse function. Guys, all these sequence of steps right here, you're gonna see that over and over this year. You need to master them, okay? Alright, so please do number 7. I'm gonna do number 8 now. Alright, that's the last example I'm gonna do. You're gonna do number 9, which is a little bit more challenging, I think. Alright, number 8 rather, sorry. F, this is a domain and this is a range. I'm not sure why, we'll see why, okay? And I need to find the inverse, so this is the given function, negative 4 square root of 2x plus 3 minus 5. And the first step is to switch x and y. So x equals negative 4 square root of 2y plus 3 minus 5. Okay? So then we solve for y. So the first thing that you do is move the 5. So I have x plus 5 equals negative 4 times 2y plus 3. And here I could, let me divide by negative 4. Okay, so x plus 5 over negative 4 equals square root of 2y plus 3. And here, of course, to grab the y, you need to square both sides. And we have what? We have that 2y plus 3 equals x plus 4 squared. I'm not going to expand that. Over 16, right? Negative 4 times negative 4 is 16. And so y equals, so I'm going to do the minus 3 and I'm going to divide by 2. So, and divide by 2, the 1/2 will be right here. So it's x plus 4 squared over 32 minus 3/2. Please take your time, make sure you can check this out. Don't forget the last step. F inverse is x plus 4 squared over 32 minus 3/2. I still don't understand why I had this domain and range restriction. Well, actually I do, okay, of course. Hey guys, what is this? What's a graph of this function? This is a quadratic equation, therefore the graph is a parabola. And actually this is a very nice form the way I give it, right? Because I got my vertex, so it's something like this. The parabola is something like this right here. And you can see that this function does not passes the horizontal line test. Therefore, it doesn't have an inverse. So what does this means right here? This is a way to restrict it. I restricted my domain by canceling all of that and just looking at this piece of the graph. And that piece passes the horizontal line test, and that is the piece that has an inverse. Okay? All right. Thank you for watching.